Hello, my name is McGuire Hodson, and this is my lab report for Lab 2, Motion of a Falling Object. The purpose of this lab is to observe the motion of a projectile, analyze the data using Tracker, and compare it with two computational models. This lab is based upon Newton's second law of motion, that force is equal to mass times acceleration, and the momentum principle, which states that the change of momentum is equal to the net force times the change in time. The first computational model depicts the expected motion of an object experiencing only gravity that follows Newton's second law. The second model displays the expected motion of an object experiencing gravity and drag. It follows the momentum principle, which accounts for both of these forces. The analysis showed the object's trajectory graph is almost perfectly parabolic, which matches the first model's predictions closely, confirming that it did indeed have projectile motion. To validate the results of the experiment, two computational models were made using VPython. The first includes only the effects of gravity and follows Newton's second law. The second one includes both the effect of gravity and the effect of drag, and it follows the momentum principle. Both programs have a ball started at a position of 0, 1, 0 meters and a velocity of 3, 5, 0 meters per second. The position updates using the position update formula, and the velocity updates using the velocity update formula. For the second model, the drag force formula used is F drag equals negative BV squared times the velocity vector. The assumptions of the first model are that gravity is the only force acting on the object, and that the object experiences a uniform acceleration of negative 9.81 meters per second. The second model assumes that gravity and air resistance are the only forces acting on the object, and that the drag force always directly opposes motion. The first model is used because it can predict motion in a hypothetical vacuum, and it shows how close the experimental data fits the prediction. The second is used to more closely approximate the experimental data. Both laws are used because these laws are also followed in the experiment. The system being analyzed is a wadded up paper ball, while the surroundings are the environment, which include air resistance, gravity, and the hallway outside the lab room. For this experiment, the object is pushed along the track with an initial velocity around 2 meters per second and a position of 1.469 times 10 to the negative 4 meters. For the models, the object has an initial velocity of 3, 5, 0 meters per second and a position of 0, 1, 0 meters. Gravity is 9.8 meters per second squared, and the drag coefficient is 0.1. The experiment involved tossing the ball into the air and measuring the distance it traveled until it reaches the x-axis, which in this case is a ruler. The coding for the computational models involves starting the ball at the aforementioned initial conditions and computing its trajectory in time increments of 0.01 seconds. For the second model, the drag coefficient was included. After collecting the data using Tracker, the motion closely matched the theoretical motion predicted using the computational model. The experimental trajectory graph showed the motion as parabolic, with a correlation coefficient of 0.9972, which is very high. The motion of the paper follows the model with gravity much closer than the one with gravity and drag. All models plot y position in meters versus x position in meters. So the computational model on top shows the effects of only gravity, the one on the bottom shows the effect of gravity and drag, and the one on the right shows the experimental data. The experimental data followed the computational model with only gravity much closer than the one with drag, because the paper ball did not experience much air resistance. This is because it was thrown indoors at a low speed and at a short distance. Although the experimental graph was mostly parabolic, it was not perfect. This is due to a variety of possible sources of error, which include some air resistance, a net force upon tossing the paper, and some measurement inaccuracies in the Tracker software. These errors are to be expected because air resistance is a force that acts upon all systems not in a vacuum, including this paper ball. So, despite the errors in the experiment, the overall motion of the paper ball was consistent, which supports the idea that no net force aside from gravity results in projectile motion when an object is thrown. The second computational model that includes the effect of drag predicts terminal velocity, but the first one does not. To experimentally find this, you could drop a ball outside from the top of a tall building. If the object was thrown straight up with the same initial speed, the time it takes to reach the ground would be longer than in the original experiment, because more time would be spent to reach the peak, and air resistance slows the object more on the way up than on the way down. The total time would be given by 2 times the initial velocity over g. Since the initial velocity would be greater when throwing the ball straight up, the total time would also be greater. Overall, the lab successfully demonstrated projectile motion using a combination of experimental data and computational models. Both the tracker data and the first VPython model showed a parabolic position-time relationship, reinforcing Newton's second law. The second model had a flatter trajectory, reinforcing the momentum principle. And that's the end of my lab report.